In this section, we're going to continue with the idea of hypothesis testing, but this time we're going to do with proportion. And all of this concept is going to be very similar to what we've been working on in section 8.2, which is hypothesis testing with sigma is known. The only difference is our test statistic, but everything else should be the same. So there's two ways to perform hypothesis testing. There's critical value method, and then there's the p-value method. So right now we're going to talk about the critical value method, and then later on we're going to talk about doing hypothesis testing for proportion using the p-value method. So before we begin, I want us to remind ourselves about some notation that we've been working with. So p is just the population proportion. P naught here is just the population proportion specified by our null hypothesis. So P naught is just the value that we're working with in our testing. X is just the number of the individual who we care about. N is the sample size, and P hat is the sample proportion. And if you recall, to compute P hat, it's just going to be X over N, where again X is just the number of individual who we care about, and N is the sample size. So our test statistics is going to be different since we're working with proportion. So here our test statistic is going to be Z is equal to P hat minus P naught all over the square root of P naught times 1 minus P naught all over N. So let's do a couple examples of how to compute our test statistic. Okay, example 1. In a simple random sample of 80, there are 54 individuals in the category of interest. First step, we want to compute our sample proportion, or our p hat. P hat. And this is going to be equal to X over N, where X is the value, the number of individuals who we care about. Here, they gave us our sample size, which is 80. So here N is 80. N is equal to 80. And here X is going to be 54. So our sample proportion is going to be 54 over 80, which is equal to 0.675. So let's say we're working with this testing here. P is equal to 0.8 versus P is less than 0.8. And here we want to compute the test statistic Z. So here we're working with H naught. P is equal to 0.8, and this is our null hypothesis, and our alternative hypothesis, H1, is going to be P is less than 0.8. Okay. So looking at our alternative hypothesis, are we dealing with a left tail, right tail, or two-tail test? Well, since this is less than, we know that this is going to be a left tail test. So left tail test. Cool. And notice that our testing is in the form of H naught, P is equal to P naught, which is P naught is just a value that we're working with. And then H1 will be P is less than P naught. So here, our P naught is just going to be the value that we're working with in our hypothesis testing, which is 0.8. So now we want to compute our test statistic Z. So here Z is going to be equal to P hat minus P naught divided by the square root of P naught times 1 minus P naught divided by N. since we know all over these values, we could just plug them in, and then we're able to compute our test statistic z. So this is going to be equal to 0.675 minus 0.8 divided by square root of 0.8 times 1 minus 0.8 divided by 80. And if you put this in your calculator, you should get negative 2.795. But we want to round this to 2 decimal places. So this should be equal to negative 2.80. So here, for this example, our test statistic z is going to be equal to negative 2.80. Okay, since we're working with the critical value method, the critical value here is just forms a boundary between the values that are considered unusual and the values that are not. So it's the same definition, but we're just working with proportion. So here, let me just split these up. So depending on whether you're working with a left tail, right tail, or two-tailed test, your critical value might be will be different. So here, your critical values will be negative z of alpha, and your critical region will be the area to the left of that critical value. And we reject, we reject our null hypothesis if z, or we reject our null hypothesis if our test statistic z is less than or equal to negative z sub alpha. And again, negative z alpha is just our critical value. And this works only if we're dealing with a left tail test. If we're dealing with a right tail test, where our alternative hypothesis will be p is greater than p naught, then we reject our null hypothesis if our test statistic z is greater than or equal to z sub alpha. And again, z sub alpha is just our critical value. And the area to the right of it is just the critical region. So if we're working with a two-tailed test, and that's when our alternative hypothesis is p is not equal to p naught, then we have two critical values actually, negative z of alpha over 2 and positive z of alpha over 2. And if we take the sum of both of these areas here, then we get alpha, which is again our significant level. So here we reject our null hypothesis if either z, your test statistic z, is greater than or equal to z of alpha over 2, or z, your test statistic, is less than or equal to negative z of alpha over 2. And all this should be very familiar. It's like what we did in section 8.2. So how do we find these critical values? How do I find these, like negative z of alpha, positive z of alpha, and positive z of alpha over 2, and negative z of alpha over 2? How do I actually find these critical values for proportion? Well, it's actually exactly the same thing when we're dealing with finding critical values for hypothesis testing when sigma is known, when our population standard deviation is known. So again, we use this little chart here, this little box, to compute our critical values. So depending on what significant level we're dealing with, and whether we're dealing with a left tail, two tail, or right tail, your critical value will be different. So this should all be just review. We want to find the critical region and critical value for the left tail test for a significant level of 0.05. We want to do it for, so this is a left tail test. we want to do it for a right tail test and a two tail test. And again, if you go back to 8.2, these values should be the same. So here we have negative z of alpha over 2. Sorry, negative z of alpha will be negative z of 0.05, which is negative 1.645. And again, I got this value from our chart. And this should be z of alpha is equal to z of 0.05, which is equal to 1.645. And for a two-tail, we have negative z of alpha over 2 is equal to negative 1.96, and positive z of alpha over 2 will be equal to 1.96. And if you remember, these values, these critical values, are just the location where, depending on whether you're working with a left tail, right tail, two tail test, they're the area of our significant level. So in this case, since we're dealing with a left tail test, this will be negative. This would be negative z of alpha will be the area to the left of this. And for this one, positive z of alpha will be the area to the right of it. And here, this will be z of alpha over 2. This will be, oh sorry, negative z of alpha over 2. And this will be positive z of alpha over 2. And then the arrow will be here. So these will be our critical region. Critical region and critical region. So it's exactly what we've been doing like in section 8.2. Nothing has really changed. The only thing that, again, the only thing that did change is our test statistic z. Okay, so now we're going to talk about the procedures of how to compute or perform hypothesis testing for proportion. Since we're dealing with proportion, our requirement might be a little bit different. So we do need a simple random sample of size n. The population is at least 20 times as large as the sample. The item in the population are divided into two categories. So usually these two are always given. However, this is important to check. Our sample proportion distribution has to be normal. And in this case, in order to check if this is satisfied, we need to check that n times p naught is greater than 10 and n times 1 minus p naught is greater than 10. If this is true, then we're able to perform hypothesis testing. However, if this fails, then we're not able to perform hypothesis testing. So let's talk about some of the steps here. So this is performing a hypothesis test for proportion using the critical value method. So we want to state the null and alternative hypothesis. This should be P, by the way. Our population proportion P. So the null hypothesis is in the form of P is equal to P naught, where P is the population proportion and P naught is just a value. It's like a number that we're working with, that we're testing actually. And then we have the alternative hypothesis can be stated in one of three ways. P is less than P naught, P is greater than P naught, and P is not equal to P naught. And depending which alternative hypothesis we're working with a left tail, right tail, or two tail test. Next, we want to find the critical value corresponding to the desired significant level, alpha. And we find this by using the table that we worked on earlier. Then we want to compute our test statistic, z. Then we want to determine whether we should reject our null hypothesis. Depending on which tests you're working with, whether a left tail, right tail, or two tail, your rejection might be a little bit different. So if we're dealing with a left tail, then we reject if our test statistic z is less than or equal to negative z of alpha. If we're working with a right tail, then we reject our null hypothesis if our test statistic z is greater than or equal to z of alpha. And again, these are just your critical values. If we're working with a two-tail test, then we reject our null hypothesis if z is greater than or equal to z of alpha over 2, or z is less than or equal to negative z of alpha over 2. And again, all these values are just your critical values. And then finally, and this is probably the most important step, is we have to state our conclusion. Do we reject our null hypothesis, or do we fail to reject our null hypothesis? And then depending on which one, your conclusion might be a little bit different. So we say that if we reject our null hypothesis, we state that we have sufficient evidence to conclude, and then input your alternative hypothesis. But if we fail to reject the null hypothesis, then we say something like, there is not enough evidence to conclude, and then state your alternative hypothesis. So let's do an example. A nationwide survey of working adults indicate that only 50% of them are satisfied with their jobs. The president of a large company believes that more than 50% of employees at his company are satisfied with their job. To test his belief, he surveyed a random sample of 100 employees, and 54 of them reported that they are satisfied with their job. Can he conclude that more than 50% of employees at the companies are satisfied with their jobs? And here, we're going to use a significant level of 0.05. Okay. So first, we want to check the requirements. We want to see if n times p naught is greater than or equal to 10. And we also want to check if n times 1 minus p naught, if that's greater than or equal to 10. If they are, then we could proceed. And notice that n here is our sample size. And we know that we had a random sample of 100 employees. So our sample size here, n, is 100. So the tricky part here is, what is p naught? Well, p naught is the value of our testing. It's like what we're using in our hypothesis testing. So maybe we should start with writing down the null and alternative hypothesis. So h naught and h1. So this is our null hypothesis, and this is our alternative hypothesis. And here we know that our null hypothesis is going to be p is equal to some value, and this is going to be p, and it's either going to be less than, greater than, or not equal to some value. But if we read the question again, he wants to know that can he conclude that more than 50% of employees at the company are satisfied? So here's his alternative hypothesis is going to be p is greater than 0.50. So that means his alternative hypothesis is going to be p is equal to 0.50. So here, 0.50 is going to be our p naught. So going back to checking the requirements, since we know n is 100, so it'll be 100 times p naught, which is 0.5 or 0.50. This is going to be equal to 50, which is definitely greater than 10. So this checks out. Now we want to check this one. So n here is 100 times 1 minus 0.50 and this is going to be equal to 50, and this is also greater than 10. So this is fine. Since both of these are satisfied, we could continue. Next, we want to compute our sample proportion, p hat. And if you remember, p hat is equal to x over n, where n is our sample size and x is the number of individual who we're caring about. In this case, 54, in our sample, 54 reported that they are satisfied with their job. So here 54 is the number of individual that we care about. So our sample proportion, our p hat, is going to be equal to 54 over 100, which is equal to 0.54. Cool. Establishing the null and alternative hypothesis. Well, we kind of already did this, but let's write this in words. What does this mean in words? What is our null and alternative hypothesis in words? So we could say that 50% of employees at the company are satisfied with their jobs. So that's the null hypothesis. But again, the president of this company is saying that no, more than 50% of his employee are satisfied with his job. So here the alternative hypothesis is more than 50% of employees at the company are satisfied with their jobs. And notice here, are we dealing with a left tail, right tail, or two tail test? Well, since our alternative hypothesis is that our population proportion P is greater than some value, we know that this is going to be a right tail test. So this is going to be right tailed. Great. Now we want to find the critical value and its critical region. Well, since we know this is going to be a right tail test, we want to find the critical value where this here value here, where the area to the right is our significant level. So here Z of alpha is going to be equal to 1.645. And again, it's the same process as we use in section 8.2 when we were dealing with hypothesis testing when sigmoid's known, when our population standard deviation is known. So next, we want to say what is the value of our test statistic Z. So what is Z here? Well, this is going to be equal to P hat minus P naught divided by the square root of P naught times 1 minus P naught divided by N. And since we know all these values, all we have to do is plug them in, put in our calculator, and then we're able to get our test statistic. So this is going to be equal to 0.54 minus 0.50 divided by the square root of 0.50 times 1 minus 0.50 divided by 100. And if you put this in your calculator, this is going to be equal to 0.80. It's always a good idea to round to 2 decimal places when computing our test statistic. So what is the conclusion? Well, since we're using the critical value method, we want to ask ourselves a question. So question, is our test statistic z greater than or equal to our critical value z of alpha? And the reason why I'm asking this question is, again, we're dealing with a right tail test. So is 0.80 greater than or equal to 1.645? Question mark. And the answer, of course, is no, because 0.645 or 1.645 is bigger than 0.80. This is a bigger number. So this is a false statement. So no, this is not true. Because again, 0.80 is actually less than 1.645. So we can conclude, thus, we fail to reject our null hypothesis H0. Great. So now we want to interpret our result, because again, this is probably the most important, because if we done all this work but we're not able to explain it in the context of the problem, then it's no use for us. So since we're fail to reject our null hypothesis, if you look up here, if we fail to reject the null hypothesis, we could say that there is not enough evidence to conclude, and then we kind of state our alternative hypothesis. So we could say here that there is not enough evidence to conclude that more than, actually, I could just copy and paste here. So I could say that there is not enough evidence to conclude that more than 50% of employees at the company are satisfied with their job. So this is an example of computing or performing hypothesis testing for proportion using the critical value method. So now we want to use the p-value method to perform hypothesis testing for proportion. So the p-value method provides more information than the critical value method. So all of this is about the same. The only difference that we're going to talk about is that in the case for proportion, our test statistic here is going to be this. But the idea still implies. So for example, when we're dealing with a left tail test, the p-value is going to be the area to the left of our test statistic. If it's a right tail, then the p-value is going to be the area to the right of the test statistic. And if we're dealing with two tails, then the p-value is just going to be the area outside of our test statistic. And then also, same conclusion, we reject the null hypothesis if the p-value is less than or equal to our significant level alpha. So it's kind of the same thing that we've been doing in section 8.2. So let me just divide this up a little bit. So if we're dealing with a left tail test, and that's when p is less than p naught, then the p-value is the area to the left of our test statistic z. And again, this is only with we're dealing with left tail test. It's just the area to the left of our test statistic. If we're dealing with a right tail test, then our p-value is the area to the right of z. And again, this is when we're dealing with right tail tests. It's the p-value is the area to the right of our test statistic z. And if we're doing two-tailed tests, the p-value is the sum of the area in the two tails. So the p-value is just the sum of the area from here plus the area from here. So that's our p-value. And that's, again, we're dealing with two-tailed tests. All of this should be just review, because it's exactly what we talked about in section 8.2. It's just our test statistic z is just a different value since we're dealing with proportion. Okay, so let's talk about the procedures or how to perform hypothesis testing using the p-value method. First, we have to check our requirement. And one of the first thing you have to check is that if n times p naught is greater than 10, and n times 1 minus p naught is greater than 10. And again, p naught is just the value that we're working with in our testing. If this is satisfied, then we're able to continue the process. So performing hypothesis testing for proportion using the p-value method. Again, we want to state the null and our alternative hypothesis. And this should be p is equal to p naught. This is the null hypothesis for proportion. Then our alternative hypothesis can be stated one of three ways. P is less than p naught, p is greater than p naught, and p is not equal to p naught. We have to find our significant level alpha. We want to compute our test statistic z. Then we want to compute our p-value. And we already had a lot of practice computing p-values because p-values is just area under curves. And we're able to use the table to find these areas. Then next we want to make a decision based on the p-value. So we want to reject our null hypothesis if our p-value is less than or equal to the significant level alpha. Then we want to state our conclusion. And this is probably, again, the most important part. If we reject the null hypothesis, then we could say something like, we have sufficient evidence to conclude, and then state your alternative hypothesis. If we fail to reject the null hypothesis, then we could say something like, there is not enough evidence to conclude, and then we state our alternative hypothesis. So let's do an example. So here, in a recent Gen X2Z American College Student Survey, 90% for female college students rated the social network site Facebook as cool. Assume that the survey was based on a random sample of 500 students. A marketing executive at Facebook wants to advertise the site with the slogan, more than 85% of female college students thinks Facebook is cool. Can you conclude that the proportion of female college students who think Facebook is cool is greater than 0.85? And here we're using a significant level of 0.05. First, we want to check the requirements. Are we even able to perform hypothesis testing? We want to check if n times p naught is greater than 10, greater than or equal to 10. And we also want to check that n times 1 minus p naught, if this is greater than or equal to 10. And here, n, since we have a random sample of 500 students, this kind of gives you an idea that n here is 500. Our sample size is 500. And p naught is the value that we're kind of working with in our testing. So maybe it's a good idea to do that first. So here we want to state our null and alternative hypothesis. So h naught would be p is equal to some value, and our alternative hypothesis will be p is either less than, greater than, or equal to some value. But if you look up here, we want to say that, can you conclude that the proportion of female college students who think Facebook is cool is greater than 0.85? So that kind of gives you an idea of like what your alternative hypothesis is going to be like. So this is going to be greater than 0.85. So that means our null hypothesis will be equal to 0.85. So here our P naught is going to be 0.85. So if we come back here, we could check that n is going to be 500 times P naught, which is 0.85, and this is going to be equal to 425, which is greater than 10. Now we have to check this part. 500 times 1 minus 0.85. And this is going to be equal to 75. And this is definitely greater than 10. Cool. Now that we know that these two satisfied, we're able to perform hypothesis testing. First, we want to compute our sample proportion, our p hat. If you remember, p hat is x over n. Well, if you look back at the question, they say here that in this random sample, they already surveyed these 500 students, and 90% of them, of female college students, rated the social network Facebook as cool. Since that's what we're working with, 90% is going to be our sample proportion. So sometimes in the question, they kind of give you the sample proportion. So here, this is going to be equal to 0.90. And we already stated the null and alternative hypothesis, but remember, here, are we working with a left tail, right tail, or two tail test? Since our alternative hypothesis is greater than, this kind of gives you an idea that we're working with a right tail test. So right tail test. And then what is our null and our alternative hypothesis stating in words? What do they mean? Well, we know that our alternative hypothesis is saying that more than 85% of female college student thinks Facebook is cool. So that's what we're working with. So in our null hypothesis, we could say that 85% of female college students thinks Facebook is cool. Okay. What is the value of our test statistic? What is Z? So remember, Z is going to be equal to P hat minus P naught divided by the square root of P naught times 1 minus P naught divided by n. Since we know all these values, we just plug them in and just insert it in our calculator. So this is going to be equal to 0.90 minus 0.85 divided by the square root of 0.85 times 1 minus 0.85 divided by 500. And if you put this in your calculator, you should get 3.13112. But we want to round to 2 decimal places. So here, this is going to be equal to 3.13. So our test statistic, Z, is equal to 3.13. Great. Now we actually want to find our p-value. Since we're dealing with a right tail test, our p-value is going to be so this is the area to the right of our test statistic. So here it's 3.13. So we want to find this area here. And it's because we're dealing with a right tail test. So in other words, we want to find P of Z greater than 3.13, but this is the same as saying 1 minus the probability of Z is less than 3.13. And we already know how to compute this. We know how to find area on the curves using the table. And again, if you still have trouble with this, you can email me or just come by my office hours because this is pretty important. So this is going to be 1 minus 0.9991. And I got this value from the table. And this would be equal to 0.0009. So our p-value is going to be equal to 0.0009. Great. So now, what is our conclusion? Well, this is asking, do we reject or fail to reject our null hypothesis? And for that, we need to ask a question. So a question. Is our p-value less than or equal to our significant level, alpha? So this is saying like, is 0.0009, is this less than or equal to 0.05? Question mark. And the answer is yes. Yeah, because 0.0009 is a smaller number than 0.05. And this is our significant level. So this is a true statement. So yes. So that means, thus, we reject our null hypothesis. So that's our conclusion. Great. So final step. We want to interpret the result in the context of the problem. So it doesn't matter if we got, doesn't matter if we did all this work. If we're not able to explain this in words what we mean, then it's kind of, it doesn't benefit everybody. So here, since we're rejecting our null hypothesis, we could say something like, we have sufficient evidence to conclude that, and we could go up here and grab our alternative hypothesis, our statement here. So we could say that we have sufficient evidence to conclude that more than 85% of female college students thinks Facebook is cool.